Hey there, today we're going to start Unit 4A. We've been learning about how to use proportions and how to use dimensional analysis to solve quantitative problems, and now we're going to get back into chemistry and blend two things together, and that is the way we count atoms and the way we measure. So there's going to be a connection here between mass, which we measure in the laboratory, and moles, which is how chemistry actually happens. The foundation of what we're about to do lies in the idea of atomic mass. The atomic mass is the mass of an average atom of an element. Atoms, even of the same element, don't all weigh the same, but there is an average atom, and when we deal with atoms in real life, in large samples, it's the average atom that we're working with. Now, if we were measuring in kilograms, or even a smaller unit like grams or milligrams or even micrograms, we would have numbers that are so small that it would be ridiculous to work with. So there's a special unit that's been developed just for talking about the masses of atoms, and it is called the atomic mass unit, or for short, AMU, or sometimes just U. Here's how it's defined. One atomic mass unit is exactly 1/12 of the mass of an atom of carbon-12. So let's think about what's in carbon-12. Carbon has an atomic number of 6. The mass number 12 means that there would be a total of 12 protons plus neutrons. So that means there are 6 protons in here, and there must also be 6 neutrons. And an atom of carbon-12 would also contain 6 electrons. So if you could add up the masses of all 3 of these particles, divide by 12, you'd have one atomic mass unit. Now, most of the mass is concentrated in the nucleus, in the protons and the neutrons. But the electrons do weigh a little bit. And so we see that an AMU is approximately the mass of a proton or a neutron, but not exactly because of the small weight of electrons that's added in there. You can find the average atomic masses of all the elements by looking at most periodic tables. Here are squares from 3 different periodic tables, and you can see the numbers here that indicate average atomic mass. For iron, 55.847. Here it is for sodium, 22.990. For carbon, it's 12.01. Different tables are going to have slight variation, but they're going to agree for the most part on what the atomic masses are. And every element on a decent periodic table has got this piece of information in it. Now, of course, most chemicals don't just exist as elements. They're part of a compound. So the mass in atomic mass units of one molecule, if it's a molecular compound, or one formula unit, if it's ionic, is called its formula mass. We can find formula mass by just adding up the atomic masses of all the atoms in the compound. For example, say we wanted to find the formula mass of ammonium nitrate, NH4NO3. Well, here's what ammonium nitrate is made of. I've got 2 nitrogens, I have 4 hydrogens, and I have 3 oxygens. So I'll need to find the atomic weight of those 3 elements. Let's go to a periodic table and do that. I'm using the touchspin periodic table that you can find online. For nitrogen, I find out that it's 14.007 approximately. For hydrogen, if I highlight that, I find out that the atomic weight is 1.008. And if I highlight oxygen, I see that it's 15.999. So keeping those things in mind, I'll go back and solve my problem. So I've got 2 nitrogens, 2 atoms at 14.007 AMUs per atom. I've got 4 hydrogen, so that would be 4 at 1.008 U's apiece. And for oxygen, I've got 3 at 15.999 U's. As you're following along with these notes, I would recommend that you have your own periodic table available so you can quickly find out where these numbers are coming from. If I add all this up, here's what I find. I come up with 80.043 AMUs. You try this one. Well, here's your answer. What we're trying to find here is Cu3PO4 2. We're trying to find the formula mass for that. Well, here's what's in there. I've got copper, 3 atoms. I've got phosphorus, 2 atoms. And I've got oxygen, 4 times 2, or 8 atoms. Well, let's find out what their atomic weights are. Highlighting copper, I see that it's 63.546. So I'll be multiplying 3 times 63.546 use. Phosphorus, 30.974. So I'll be multiplying phosphorus 2 by 30.974 U's. And we looked up oxygen earlier and find that it's 15.999 U's. So I'm going to sum all this up to get my overall formula weight. And that comes out to 380.578 U's per formula unit. The atomic mass unit is a really good unit to use when you're talking about individual formula units or individual molecules or individual atoms, but that's mostly theoretical. In real life, we are usually measuring samples that are much larger than that, and so it's practical to measure things in grams. That's what our balances read in, and it just makes sense to have some way to go back and forth between moles or fundamental units and grams, which is what we have to use in the laboratory. The tool that we use for that is something called molar mass. It turns out that a mole, we think of it as 6.022 times 10 to the 23rd units, but a mole is formally defined as exactly the number of particles in exactly 12 grams of carbon-12. I think we had that definition earlier in the year. Well, since 12 AMU is also defined based on carbon-12, it turns out that there's not an accidental relationship between the AMU and the mole. The formula mass, or the atomic mass if it's an element for a substance in U's, in atomic mass units, is the same exact number as the mass of a mole of the substance in grams. So for example, if I look up iron in the periodic table, I find out that iron has an atomic weight of 55.847 atomic mass units. That's what one atom of iron weighs. However, that number means something else. It's 55.847 grams for every 1 mole of iron. Same number, but it has two different uses with two different units. The same thing is true for compounds. Water has a formula mass of 18.015 atomic mass units. 1 molecule of water weighs that amount. But 1 mole of water molecules weighs 18.015 grams. So there's a dual purpose for these numbers. When it's written this way, we call this the molar mass, the mass of 1 mole. Molar mass is an important problem-solving tool. This is extremely important. You're going to use this over and over and over again repeatedly, so get used to using it to go back and forth between mass, which is what we do in the lab, and moles, which is theoretically how everything happens. So we need to go back and forth between our chemical theories and the realities of the lab by using molar mass. It's our link that goes between the two. There are two ways that we can do this. One is through proportions, the simple thing where you cross multiply and divide. And the other one, the one that you're going to see me using much more often, is using dimensional analysis with molar mass as a problem-solving tool. So let's go through both methods just so you can see how they're done. The first one is proportions. Let's say we had this problem. What is the mass of 0.350 moles of water? Well, I could set up a proportion like this. First of all, if I find the molar mass of water, I would do that by taking 2 times the molar mass of hydrogen, and that's 1.008 grams per mole. We looked up that atomic weight earlier. And 1 times 15.999 grams per mole. We looked that up earlier too. If you're having trouble wondering where these numbers are coming from, just get your periodic table out and have that handy so you can look these up. Hydrogen, you'll find 1.008. Oxygen, you'll find 15.999. If I add 2 hydrogen weights and an oxygen weight, I will find out that a mole of water would weigh 18.015 grams. That's the molar mass of water. Now that can form 1/2 of a proportion. 18.015 grams is to 1 mole as how many grams would be 2.350 moles of water. When I cross multiply and divide, I'll get my answer. 0.350 times 18.015 divided by 1. Well, X here turns out to be 6.30 grams of water. I could do this the other way. If I knew grams and I needed to find moles, I could set that up too. Here's how it works. If I look up the atomic mass of aluminum, I would find its molar mass at the same time. Aluminum, 26.982, the periodic table says, grams per 1 mole. So, if I had 15.0 grams of aluminum, how many moles would I have? That's X. Cross multiply and divide to find X, and I would find the answer to be 0.556 moles of aluminum is 15 grams. Now here's a technique that I like a lot more, dimensional analysis. And when you start doing more complex problems with this, you'll find out why dimensional analysis is a better method. Let's do the same problem, only using dimensional analysis. Molar mass as a factor in dimensional analysis. Here's how this works. The question is the same question. What's the mass of 0.350 moles of water? My starting point is this. I write down what I'm given. The given information here is 0.350 moles of H2O. And like all dimensional analysis problems, I want to multiply by factors that are equal to 1 until I get the unit that I want. In this case is grams, because the question is what is the mass? Well, molar mass is the factor that can allow me to do that. I have just calculated that 1 mole of water has a mass of 18.015 grams. That's the molar mass. So molar mass here is being used as a dimensional analysis tool. 18.015 grams is 1 mole. So I'm just multiplying by 1. I don't change the quantity of matter. But now instead of it being expressed in moles, it's expressed in grams because the moles cancel out. When I take 0.350 and multiply by 18.015, well, it's the same arithmetic that I did before. So I still get 6.30 grams. This method works great. How many moles are in 15 grams of aluminum? We've had this problem before. We solved it with a proportion. Now let's do it with dimensional analysis. Again, I start out by writing down what's given to me, 15.0 grams of aluminum. My target is what I'm asked about, and that is moles. How many moles of aluminum? Molar mass is the link. Molar mass is the conversion factor. I know for aluminum that 26.982 grams is the same thing as 1 mole. By putting the grams on the bottom this time, they now cancel out, and the unit that I have left is moles. I take 15 divided by 26.982 to 3 significant figures. I get 0.556 moles of aluminum. You try one. Well, the first thing you have to do is figure out what the molar mass of carbon dioxide is. Carbon, there's 1 mole of it, and its molar mass is 12.011 grams per mole. And the oxygen, there are 2 moles, and it's 15.999 grams per mole. When I sum all this up, I get 44.009 grams per mole. This is the molar mass of CO2. Now, to solve my problem, 0.0052 grams of CO2 is my starting point. That's what's given to me. What I want to find out is how many moles of CO2 is that. Molar mass is my link. Carbon dioxide I have determined is 44.009 grams for every mole. With grams on the bottom, they now cancel out. When I multiply together, the only unit I'll have left is moles of CO2. The arithmetic of actually solving this is to take 0.0052 and divide by 44.009, and the answer that you get is 1.2 times 10 to the negative 4th moles of CO2. Here's another one. The question here is, what is the mass? The given information is 2.5 moles of H2. We're trying to get to grams of H2 because that would be mass. Again, molar mass is the link. H2 means there are 2 atoms of hydrogen. Hydrogen is 1.008 grams per mole, but if we multiply that by 2, we get 2.016 grams per mole. That's the molar mass of H2. Well, I want moles on the bottom, so I put 1 mole down there. That'll allow moles to cancel. I want grams on the top because that's got to be in my answer, so I put my 2.016 grams up on top. With moles canceled out, I will end up with only grams of H2O. 2.5 times 2.016 comes out to 5.0 to 2 significant figures, grams of hydrogen. You can use dimensional analysis for extended calculations, and that's really the beauty of it. The problem that I'm about to do would require two sets of proportions, but only one dimensional analysis setup. The question is, how many atoms are in 15 grams of aluminum? Again, I start out by writing down the given information, 15.0 grams of aluminum. Where am I going? The target is, how many atoms of aluminum are there? Well, the first thing I can do is get into atomic type units by changing grams into moles. I know that aluminum is 26.982 grams per 1 mole. So I can multiply by this factor and keep the same amount of aluminum, but change from grams to moles because grams cancel. Now here's something else I know. Every 1 mole contains 6.022 times 10 to the 23rd of any unit, in this case atoms. So by multiplying by this factor with the mole quantity on the bottom, I now cancel with the moles that were there before. The only unit that's uncancelled is atoms of aluminum. So I take 15, multiply by 6.022 times 10 to the 23rd, divide that by 26.982, and I end up with 3.35, three significant figures, times 10 to the 23rd atoms of aluminum. So another example. Iron has a density of 7.86 grams per milliliter. That's a fact. How many moles is in 5 milliliters of iron? I write down my given information. I'm starting from 5.00 milliliters of iron. What I want to know is, how many moles of iron is that? Well, to get from milliliters into grams, I can use density as a conversion factor. 7.86 grams is 1 milliliter. That's what the density means. By multiplying by this factor with the milliliter on the bottom, I cancel it out and I get grams. Well, here's what else I know. If I look on the periodic table, I find that iron is 55.847 grams per 1 mole. By putting the grams on the bottom in this factor, they cancel. I end up with moles of iron as my unit. Now that my unit is right, I know that doing this arithmetic will give me the correct answer. 5 times 7.86 divided by 55.847, I'll end up with three significant figures in my answer, and it's 0.704 moles of iron.